Welcome to Team Animus Ferus' Flight Readiness Review. This year we built a UAV capable of operating accurately at high speed to accomplish autonomous flight, waypoint navigation, obstacle avoidance, and airdrop. Animus Ferus built Spirit 11, a complete redesign over past UAVs, to accomplish our objectives in the most point-efficient manner possible. Spirit 11 is a hexacopter design that builds upon previous success as well as current research and technology. Animus Ferus is confident in its ability to achieve a competitive overall score. Now let's meet the competition team members.
Hello, my name is Devin Host. I'm a junior at Flint School. This is my second year on the team. I have experience working with UAS technologies. During both development and on the flight line, I am the team captain.
My name is Ethan Wood. I'm a senior, and this is my second year on the team. I have experience with UAS technologies. During development, I was the hardware sub-team leader, and on the flight line, I will be monitoring for any hardware-related concerns.
My name is Owen Krause. I'm a junior. This is my second year on the team. I have experience with UAS technology. During development, I was the head of the software sub-team.
My name is Charles Stewart. I'm a senior, and this is my first year on the team. I have limited experience with UAS technologies. During development, I was the communications officer, and on the flight line, I am monitoring environmental concerns.
My name is Zach Pavis. I am a junior. This is my first year on the team. I have limited experience with UAS technologies. During development, I was a part of the hardware sub-team, and on the flight line, I am safety officer.
My name is Jacob Trent. I am a senior. This is my first year on the team. I have limited experience with UAS technology. During development, I was on the hardware sub-team, and on the flight line, I'm GCS operator.
My name is Anton Tiapkin. I'm a senior, and this is my first year on the team. I have limited experience with UAS technologies. During development, I was on the hardware sub-team.
My name is John Canarium. I'm a senior, and this is my first year on the team. I have limited experience with UAS technologies, and during development, I was a member of the hardware sub-team.
My name is Thomas Norberg. I'm a senior. This is my first year on the team. I have limited UAS experience. During development, I was a member of the hardware sub-team.
My name is Ben Spivey. I'm a junior. This is my first year on the team. I have limited experience with UAS technologies, and during development, I was a member of the hardware sub-team.
My name is Armand Kumar. I'm a junior, and this is my first year on the team. I have limited experience with UAS technologies. During development, I was a member of the software sub-team, and on the flight line, I am interop connections manager.
My name is Shiv Sharma. I'm a junior. This is my first year on the team. I have limited experience with UAS technologies, and during development phase, I was part of the software sub-team.
Spirit 11's propulsion system comprises KDE's 7215XF 135 kV motors, UAS 85 UVC ESCs, and 24.5 by 8.1 inch pitch folding carbon fiber propellers. Each motor propeller pair is capable of producing 30 pounds of thrust for a total thrust to weight ratio of 3.6 to 1 with the planned payload. To complement this new high thrust propulsion system, a redesigned electrical system was needed to ensure safe and efficient operation of the UAV. Spirit 11 is powered by four 23,000 mAh 7-cell LiPo batteries, two of which are wired in series to create two 14S 23,000 mAh packs, which are then wired in parallel to create a 14S 46,000 mAh system. These four batteries are fixed to the frame via a custom battery case that allows for the team to quickly secure them directly to the frame with a latching mechanism. This case is comprised of a top plate made from 1.5mm thick carbon fiber, along with 3D printed walls extruded from a carbon fiber reinforced nylon filament. The batteries themselves are surrounded by the same carbon fiber reinforced nylon filament to form a shell that protects the fragile cells against damage during insertion or removal. In competition configuration, the Spirit 11 UAV weighs 49 pounds at takeoff, including the UGV, with a diameter of 54 inches. A plate to secure the UAV payload was designed using 3K carbon fiber and 3D printed components to hold the UGV securely and release consistently. It implements a single servo and pin to interface with the UGV, along with four stabilizing posts to secure the payload during transit to the drop location. A DC motor is also implemented on the payload plate to retrieve the free-hanging tethered line from the descended UGV. Both the airdrop and flight systems are controlled by the onboard autopilot. Spirit 11 features the Pixhawk 2.1 autopilot, which is widely used at both consumer and industrial levels due to its reliability, ease of use, large support community, and developed suite of features. The autopilot is supported by dual GPS and compass modules, which provide the UAV with greater positional accuracy and redundancy in case of a component failure. The autopilot features a full suite of redundant internal sensors as well as 2 separate power supplies. With the implementation of the UGV, the communication system used throughout the UAS needed to be updated. The communication system now includes 3 RFD900X radios set up in a multi-point configuration operating on the 915 MHz band with 128-bit encrypted communications between the GCS, UAV, and UGV. A FR-Sky X8R receiver and Taranis X9D Plus transmitter operating the 2.4 GHz band allow the safety pilot to take control of the craft. On the ground, the team uses Mission Planner and the MAV proxy communication protocol to interface with the drone and receive telemetry data. This data is transmitted to the interoperability server and displayed on the team's competition viewer, a web-based UI that displays all of the competition elements for both the team and judges' use. Through extensive point analysis, the team decided to abstain from the object detection, classification, and localization portion of the 2019 competition. Based on experience from the 2018 competition, we found that our current image system, which is built off the open source platform OpenCV, is not accurate enough to offset the points lost due to the mission time points penalty. Last year we received 13 points from the ODCL portion of the competition, but spent 9 minutes gathering pictures and processing them. Thus, the resulting point value from the ODCL portion yielded a net loss for our total score. Therefore, we will not be covering any ODCL or imaging related systems or test results in this review. We will now go over what is expected of Spirit 11 in the 2019 competition. Autonomous flight will be attempted with high confidence. Obstacle avoidance will be attempted with high confidence. Object detection, classification, and localization will not be attempted. Airdrop will be attempted with overall high confidence. We have medium to high confidence in drop accuracy within 5 feet due to environmental concerns such as wind. High confidence in the payload surviving the drop, and high confidence in the UGV's ability to accurately drive to location. During development, the team used test-driven development strategies to ensure all components of the craft would perform appropriately during the mission demonstration. When possible, each component was tested in simulation, unit or individually tested, implemented on the test platform Spirit 10, and finally integrated into Spirit 11 for final testing. This testing methodology allows for multiple components of the UAS to be constructed simultaneously, as well as the reduction of variables, as each test consists of core components. In total, the team completed more than 200 hours of individual component testing. Following the exceptional performance and reliability of the Spirit 10 UAV, the team wished to again emphasize reliability and redundancy as cornerstones for the developmental and testing process. Therefore, each test of the UAS was designed to further improve or optimize one or multiple of the following criteria: safety, performance, redundancy, and reliability. The first of these developmental tests were simulation tests conducted in Fusion 360 CAD software. Here, the team used multiple stress analysis tests to optimize the weight of the airframe while ensuring safety and structural integrity was not compromised. The large mass of the UAV posed a unique developmental challenge as many components needed to withstand increased forces. These simulation tests were then confirmed by real-world stress tests using 30-pound weights on each of the spars of the fabricated airframe. The carbon fiber structure performed excellently and had minimal deflection under the large 180-pound load. The thrust output of the propulsion system was tested on a new high-thrust prop tester from which the team was able to capture real-world thrust and power readings from the load cell and integrated sensors. The team was able to verify that although this propulsion system is less efficient than that of last year's craft, the thrust output per motor has tripled from 10 pounds per motor on Spirit 10 to now 30 pounds per motor on Spirit 11. Aircraft speed and range was another key developmental test conducted by the team, as these elements are of paramount importance for the 2019 competition. Following a point analysis of the 2019 rules, the team identified that a sub-20-minute mission would provide the greatest mission score. Spirit 11 was designed to fly farther and faster than the team's previous craft, Spirit 10. Initial range and speed calculations were performed using the software eCalc, which takes into account many propulsion variables. Spirit 11's maximum speed was projected to be 40 miles per hour and a maximum flight range projected of 7 miles, a significant upgrade over Spirit 10, which had a maximum speed of 25 miles per hour and a maximum flight range of 4.3 miles. These calculations were corroborated by flight tests in which the team gradually increased the UAV's cruise speed to an optimal speed of 33 miles per hour. The range calculations and flight tests showed that at this speed, the UAV would both have the range and speed required for a high-scoring mission demonstration. As of recording, the Spirit 11 UAV has over 50 autonomous flights, each with less than 5% of the total time spent in manual mode. Manual control is required for the start of every flight to issue the arm command and to spin up motors to 30% throttle before entering autonomous navigation. The UAV underwent an extensive tuning process in which the PID rates were altered to ensure proper pitch, roll, and yaw responses from commands issued by the autopilot. This process helped ensure the accuracy of waypoint navigation, as well as increases the operational safety of the UAV as tuning helps to eliminate unexpected behavior. Spirit 11 is capable of autonomous waypoint capture and navigation. After extensive testing, the UAV was able to capture 99% of the 200 plus autonomous navigational waypoints with an accuracy within 4 feet. Obstacle avoidance is accomplished via the manual plotting of avoidance waypoints during setup time. Here, the team utilizes our competition viewer to visualize the simulated obstacles so that the UAV path can be altered. The UAV treats these avoidance waypoints the same as navigational waypoints. Therefore, unit and simulation testing of this system was not necessary. Of the 10 simulated obstacles tested, the UAV was able to successfully avoid 9. Flight tests showed that the UAV is capable of flying these avoidance paths with high precision, and the team predicts that the UAV will be able to avoid greater than 90% of the simulated obstacles during the mission demonstration. During the initial design phase, the team attempted to design an airdrop system that would safely and accurately deliver our UGV Veil 1. The team constructed a prototype model and eventually a full-scale system to gently lower the UGV from the UAV using a friction clutch system. The drop system was extensively unit tested indoors at a reduced height of 16 feet with over 30 trials yielding an average accuracy of 1 foot. The unit testing of the friction clutch provided mixed results as the mechanism was seemingly inconsistent with the drop speed delta of plus or minus 4 feet per second. The team mitigated this problem by identifying the correct drag setting on the reel after extensive tuning. Once tuned, the system was then mounted on Spirit 10, the test platform for testing at the desired altitude. Furthermore, these drop tests from Spirit 10 did not include the UGV, but rather a simulated mass, equal to the weight of the UGV. The first of these tests proved promising with an initial accuracy of plus or minus 3 feet over 5 trials from the desired drop location using the simulated weight and from an altitude of 100 feet. Following the success of the airdrop mechanism during unit testing and on the test platform, the team moved forward and mounted the delivery mechanism on Spirit 11 with a simulated mass. Here, the team conducted 3 tests with an accuracy within 3 feet from drop location. The air delivery mechanism failed 2 times during the tests on Spirit 11 due to the drag setting not having been set correctly. The team corrected this setting before conducting further drop tests. In total, the air delivery mechanism was tested from an altitude of 100 feet 10 times with an 80% success rate. All successful air deliveries had an accuracy within the 5-foot target for an average accuracy of 3.7 feet. The UGV has a 100% navigational success rate over the 20 waypoints tested with an accuracy within 2 feet from the desired location. Team Animus Ferus conducted a total of 5 mission tests. During the first mission test, the air delivery mechanism failed unexpectedly. The self-regulating friction mechanism failed to release the UGV the entirety of the 100 feet. The UGV descended 50 feet before the tether stopped releasing and the UGV remained suspended from the craft in mid-air. The UGV was then released by the mechanism during the UAV's return to launch outside of the squirrable drop zone. The UGV was also catastrophically damaged and needed to be rebuilt. The team took this time to further evaluate the air delivery mechanism and identify the root cause of the failed drop. After careful analysis, the team came to the conclusion that by having the spool of line run through multiple channels on the payload plate of the UAV, excess friction and drag was placed on the device that was not accounted for during unit testing. Therefore, the air delivery mechanism was changed to have the spool of line on the UGV to eliminate any excess friction in the air delivery mechanism. The team also installed a DC motor onto the payload plate to rewind the tether after the UGV made contact with the ground. The line is rewound to decrease the time needed for resetting the mechanism between tests and ensure that the motors would not become tangled during landing. Following these changes, the team has 100% success rate in the airdrop category, including drop accuracy and the UGV drive to location. The mission tests were assessed using the percentage structure provided by the 2019 rules. In 5 mission tests, the team scored an average of 98% in timeline, 99% in autonomous flight, 93% in obstacle avoidance, 0% in ODCL, 80% in airdrop, and 98% in operational excellence. Following these tests, Team Animus Ferus expects a score of 79% of total mission points at the 2019 mission demonstration and a placement within the top 5 teams. Thanks for watching, and we look forward to a successful mission demonstration in June.